Well, you take a Lagrangian that can describe the motion of a one-dimensional entity through space-time. And you take that two-dimensional Lagrangian, and within it there's a field, X, that maps the world sheet of the string into the ambient space-time. And the action that describes this motion is basically the area of the world sheet using the pullback metric from the ambient space-time to the world sheet of the string. And then by using, of course, the standard sum over paths approach to quantum mechanics developed by Richard Feynman, we can work out correlation functions in this two-dimensional field theory, and those in principle would be the observables that describe the scattering amplitudes of strings in string theory. How's that?
Okay, yeah, right here.
Curious, what's your opinion on M theory or string theory? That is to say, do you feel that it could be the, theory of unification, or is it just a theoretical pipe dream, in your opinion?
Right now, it's smelling a lot, smelling pipe dreamy, I think. I've been following these guys for 27 years. And every 5 years, I ask them, how much longer? And they say, just a couple more years. And I asked them every 5 years. Just a couple more years. So I did this in 1982, 87, 91, and so something's wrong here. And they said, well, it's a hard problem to unify all the forces of the world and put everything under one equation and make it all the beautiful vibrating strings. It's hard. That's the answer they give, rather than, we're just too stupid. General relativity was hard. It was done by one man. It took him 9 years. We had experimental proof 3 years later. I'm ready for another idea from them. But they're the only game in town, and they're really inexpensive. You just buy a few pencils for them, maybe a sharpener. They're good to go. Throw in a laptop. Fine. They're not in anybody's way. So I'm okay with that. Okay? But I'm no longer their champion. I used to speak praises of them. And just because they want it to be elegant doesn't mean the universe agrees, right? Most efforts to layer onto the universe our own sense of what is elegant have failed from the very beginning of thinking about the universe. So I'm losing my confidence, but I don't volunteer that fact. It has to be asked of me, as you just did. Okay.
What is stuff made of? What are the basic fundamental ingredients inside of all of the matter that we encounter in the world around us? If you take any piece of matter, say a block of wood, if you cut it in half, cut that remaining piece in half again, and keep on cutting ever smaller, we all pretty much know that you get to molecules, and then you get to atoms, which make up molecules, and we also know that the atoms are made of finer constituents, electrons that are in these quantum orbits, these quantum clouds around the nucleus, which itself has particles, protons and neutrons, and inside the protons and neutrons we found that there are even smaller particles, quarks. String theory comes along and challenges that. It says that those little tiny dot particles that we envisioned as being the basic ingredients, there's something else further inside of them. Look deeply inside an electron, deeply inside a quark. String theory posits, hypothesizes, that you'll see a little tiny string-like filament of vibrating energy. Like a string on a violin, this little tiny string can vibrate. And one vibration will, say, be an electron. A different kind of vibration, a different note, to use the musical analogy, would be an electron, a quark, or a neutrino. So in that way, all the different kinds of particles arise from the different notes that this hypothetical entity called the string can play. Everything, in a sense, is a kind of cosmic symphony. All the particles of the world are just the notes that this ingredient, if it exists, we don't know that it does, that this little tiny string can play.
We are now approaching lunar sunrise, and for all the people back on Earth, the crew of Apollo 8, has a message that we would like to send to you. In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light. And God saw the light, that it was good, and divided the light from the darkness. And God called the light day, and the darkness he called night, and the evening and the morning were the first day. And God said, "Let there be a firmament in the midst of the waters, and let it divide the waters from the waters." And God made the firmament, and divided the waters which were under the firmament from the waters which were above the firmament. And it was so. And God called the firmament heaven, and the evening and the morning were the second day. And God said, "Let the waters under the heaven be gathered together into one place, and let the dry land appear." And it was so. And God called the dry land earth, and the gathering together of the waters called he seas. And God saw that it was good.
Now, another thing that people often say is that for guessing two identical theories, suppose you have two theories, A and B, which look completely different psychologically, have different ideas in them and so on, but that all the consequences that are computed, are exactly the same. Maybe say they even agree with experiments. They add to them. The point is, though, that the two theories, although they sound different at the beginning, have all consequences the same. It's easy usually to prove that mathematically by doing a little mathematics ahead of time to show that the logic from this one and this one will always give corresponding consequences. Suppose we have two such theories, how are we going to decide which one is right? No way, not by science, because they both agree with experiment to the same extent. There's no way to distinguish one from the other. So the two theories, although they may have deeply different ideas behind them, may be mathematically identical, and usually people say then in science one doesn't know how to distinguish them, and that's right. However, for psychological reasons, in order to guess new theories, these two things are very far from equivalent, because one gives a man different ideas than the other. By putting the theory in a certain kind of framework, you get an idea what to change, which would be something, for instance, in theory A that talks about something that you say, I'll change that idea in here. But to find out what the corresponding thing is you're going to change in here may be very complicated. It may not be a simple idea. In other words, a simple change here makes maybe a very different theory than a simple change there. In other words, although they're identical before they're changed, there are certain ways of changing one which look natural, which don't look natural in the other. And therefore, psychologically, we must keep all the theories in our head. And every theoretical physicist that's any good knows 6 or 7 different theoretical representations for exactly the same physics, and knows that they're all equivalent, and that nobody is ever going to be able to decide which one is right at that level, but he keeps them in his head hoping that they'll give him different ideas for guessing. Incidentally, that reminds me of another thing, and that is that the philosophy or the ideas around the theory, a lot of ideas, you say, I believe there is a space-time or something like that in order to discuss your analysis, that these ideas change enormously when there are very tiny changes in the theory. In other words, for instance, Newton's ideas about space and time agreed with experiment very well. But in order to get the correct motion of the orbit of Mercury, which was a tiny, tiny difference, the difference in the character of the theory with which you started was enormous. Reason is, these are so simple and so perfect. They produce definite results. In order to get something to produce a little different result, it has to be completely different. You can't make imperfections on a perfect thing. You have to have another perfect thing. So the philosophical ideas between Newton's theory of gravitation and Einstein's theory of gravitation are enormous. The differences, rather, are enormous. What are these philosophies? These philosophies are really tricky ways to compute consequences quickly. A philosophy, which is sometimes called an understanding of the law, is simply a way that a person holds the laws in his mind so as to guess quickly at consequences. Some people have said, and it's true, for instance, in the case of Maxwell's equations and other equations, never mind the philosophy, never mind anything of this kind, just guess the equations. The problem is only to compute their answers so that they agree with experiment, and is not necessary to have a philosophy or argue or words about the equation. That's true in a sense, yes and no. It's good in the sense you may be, if you only guess the equation, you're not prejudicing yourself and you'll guess better. On the other hand, maybe the philosophy helps you to guess. It's very hard to say. For those people who insist, however, that the only thing that's important is that the theory agrees with experiment, I would like to make an imaginary discussion between a Mayan astronomer and his student. The Mayans were able to calculate with great precision the predictions, for example, for eclipses and the position of the moon in the sky, the position of Venus, and so on. However, it was all done by arithmetic. You count certain numbers, you subtract some numbers, and so on. There was no discussion of what the moon was. There wasn't even a discussion of the idea that it went around. There was only calculate the time when there would be an eclipse or the time when it would rise, the full moon, and when it would rise half moon, and so on. Just calculated only. Suppose that a young man went to the astronomer and said, I have an idea. Maybe those things are going around, and there are balls of rocks out, like rocks out there. We could calculate how they move in a completely different way than just calculate what time they appear in the sky and so on. So, of course, the Mayan astronomer would say, yes, how accurate can you predict eclipses? He said, I haven't developed the thing very far. He says, but we can calculate eclipses more accurately than you can with your model, and so you must not pay any attention to this because the mathematical scheme is better. And there's a very strong tendency of people to say against some idea, if someone comes up with an idea and says, let's suppose the world is this way, and you say to him, well, what would you get for the answer for such and such a problem? And he says, I haven't developed it far enough. And you say, well, we have already developed it much further, and we can get the answers very accurately. So it is a problem as to whether or not to worry about philosophies behind ideas.